Okay, let's start today's class. So, and then I believe everyone knows. So I posted the second lab assignment on the Blackboard. So actually, in the second lab assignment, you are requested to design combinational logic modules. So actually, you can try the different uh, methods to design the combinational modules. Okay. So actually, I think it's not difficult, but firstly, you need to understand the module description. So actually, you are requested to design test module, that is black box module. So please pay attention. So read thoroughly the descriptions of this module, the test black module. Then actually, so I already provide the so kernel, okay, so it means the truth table. So the Boolean equation. So you can actually add the proper equation. Actually, it means the assignment statement, this test one module. Okay, so actually it will not be difficult. And then also I provide the test bench file. Okay. So you don't need to design the test bench because we did not learn about the test bench module in this class. So we will learn. Okay, so and then actually also I provide the schematic of the combination of module. Then based on this combination of schematic, then you are requested to design the combination of module based on this schematic. Okay. And then, so actually different method to design the same module, right? And then finally, you need to design the structural module. Okay, so it means that actually the base module. So actually this 10-4 module, then I provide the base. So it means that the lower level module. So I actually designed the lower level module for the 2-to-1 module. And then actually I provide the first state gain for 2-to-1 multiplexer module. Then you can design the equivalent combination of module. It's the same to this schematic, but the 2-to-1 multiplexer is designed with the tri-state gate. Also, I want to fix some example. So actually, so this is the example 2-to-1 multiplexer tri-state gate. So 2-to-1 multiplexer implemented with tri-state gate. And then I also mentioned that in order to design the tri-state gate, the output. So this is the output of the tri-state gate. The output of the tri-state gate needs to be declared as a tri. Okay, because this signal will have high Z. So it means the high impedance output. And then also we can combine two tri-state gates to implement the 2-to-1 multiplexer. So which means that the Y is connected to each other. So it means that the output Y of this multiplexer also needs to be declared as a tri data type. Actually, it was missing the original slide. So I want to fix this slide. Okay. So actually, in the original slide, this output is declared as logic, but actually it should be declared as a tri data type because the output of this tri-state gate is also declared as a tri. So it is connected to the output of this module. So it means that the output of this module, the box tri, is also need to be declared as a tri data type. Okay, so I want to fix this slide. So So actually, I believe you can easily complete this second lab assignment. Also, so another note is that actually, so we are using the system value feature such as the always on the com, always on the FF, in the flip flop, and then always on the latch statement. But unfortunately, these statements are not supported by older version of Icarus Verilog. So if you are using the Icarus Verilog version 11, then these statements are supportive. So there are no problems. So which means that you can use is always on the com, always on the FM, and always on the next statement. But if we are using the older version, so actually if you are using the Ubuntu 22.04 version, then it's okay. So actually the basic version of the Icarus Verilog is the 11, the version 11. But if we are using the older version of the Ubuntu, then you need actually the older version will be installed. Okay. So in this case, you cannot use the each statement. So there are two methods for fixing this problem. The first method is a recommended method. You can change the always com into the always add and then bracket the start type. Okay. So and then also you can just change the always on the FF with the always. So actually I mentioned that. So in Verilog, not system Verilog, so the Verilog is the older version of system Verilog. Okay. So in Verilog, we use only always. Okay. Not always on the com, always on the FM, always on the latch. So actually, each equivalent always on the com is equivalent to always add and start. So start means the everything. So so this is the sensitivity list. So everything is that actually it monitors the every signals. It monitors the behavior of every signals. But don't worry about that. Actually, the cat2, so it means the simulator, check the input signals of the inside of array statement. If we use this everything in the statement, sensitivity list, but the cat2 automatically checks the all input signals under this array statement. Then it generates the required sensitivity list automatically. So don't worry about that. Actually, this is equivalent to the always underbar com. Also, the always underbar FF is actually you can just change the always underbar FF with the always. It is because so if you see the sensitivity list of always underbar FF, then every required sensitivity condition is already listed in the sensitivity list in always on the FF. So you can just change it always on the FF to the always. If we are using the older version of Icarus Verilog. Okay. So recommended method. And then if we want to install the newer version of Icarus Verilog on your operating system, then you can download the source code and then you can compile the downloading the source code by yourself. Then you can generate the binary file of the Icarus Verilog. This is the second method, but you need to compile the source code of Icarus Verilog by yourself. Okay. This is some notes for the lab number 2. Okay. Any question? I think it's okay. So it is not difficult. Okay. So I believe you can, if you understood what you learned in the previous lectures, then I believe you can easily complete this second lab assignment. Actually, I believe it will take less than 1 hour. Okay. Yeah. complete, no? Usually, no? But so if you encounter any problems or issues, then you can post your issues on the black not blackboard on Piazza. Also, you can ask your to TAs. Okay, so you can see. But please post your questions on Blackboard. Okay. Okay. So try to use not Blackboard. Okay. So sorry about that. Try to use Piazza. Okay. Please post your questions on Piazza. And do not. I recommend that to email the TAs. Okay. So I believe TAs receive many emails from students, but I cannot observe any posted questions on Blackboard. Not Piazza. So please post your questions on Piazza. Okay. So in the previous lecture, so we learned about the finite state machine. So I mentioned that we use finite state machine to define different states. Okay, and then the different states will generate different kinds of output. So this is the example of the statement in real world. So later repeat and guess. And then also another example is your smartphone. So smartphone operating state. So if your smartphone is operating in high performance mode, also your smartphone can be operating in idle mode, but another saving mode. So these different states will generate the different kinds of output. So actually we can observe many examples in the real world, also in real application like that. The finite state of the examples of finite state machines. Okay, so and then as you know, it's so in order to design the finite state machine, then we need to first design the state diagram. So firstly, we can define the input and output signals, and then based on the input and output signals, we can describe the state transition. We can sketch a state transition diagram based on the input and output. So we can use input signals for conditions for transition. Okay, so you can find these conditions. So if some conditions are met, the state is changed from current state to the next state, right? Then this state change is called state transition. Okay, so we can define the state transition diagram based on the descriptions, and then we can generate the state transition table based on this transition diagram, and then we can set the encoding rules for state, because we cannot use the state data type. So we need to use the binary data for describing this, for designing the systems. So its state, the state can be encoded into the binary signals, the binary data. Okay, and then so we can complete the state transition table, and then we can also define the output logic. And then based on the this design, we can implement the required modules for FSM. So FSM requires the 3 different kinds of blocks, like the combination and sequential logic. So FSM is composed of state register. So state is changing, so which means that we need to store the current state, and then based on the current state and input signals or input conditions, then next state will be decided. So we need to use the sequential logic. So I mentioned the sequential logic as memory, which means that previous event can be stored in the sequential logic. So we use the D flip-flops to implement state register. So this is the next state. The input of the state register is the next state, and then the output is the current state. Okay. And so it means that we need to implement the next state logic. So it means so based on the input, the current state and input signal can generate the next state. So input state, current state is feedback to the next state logic. And then also you can find the input signal. So using the current state and input signal, you can generate the next state. This is the output of combination. So you can define the next state logic. And we use FSM to generate the output signals based on the different states. So it means we need to generate the output signals using the output logic. Then we can implement the output logic based on the current state because this is Mealy FSM. So output signals are generated from current state only, and it is Mealy FSM. And then in this lecture, so I will also show the example of Mealy FSM. Okay, so this is also we also covers the timing diagram of FSM. So actually, this is the sequential logic. So which means actually, so it's timing. So understanding the timing diagram is also important. So which means that the signals. So you can find the clock signal. So clock signal is very important, and then click the signal is the design. And then the input signals are changed by clock cycles. What means that the input signals are changed by time. Okay? So using this action, this is the time. Then we can observe that the outputs and the states are changed by time. So it's very important. So so we are learning about the hardware system. So and then the main difference between the hardware and software is time. Okay. So we need to understand how the states or outputs are changed by time. Okay, it's important. For software is different. For software, in the software, just instructions are executed atomically. Okay, it's started and start and that's it. Okay, so software is much simpler than hardware design. Okay, so let's see the different way of state encoding. So in the example, so we have 4 different states, right? So and then in order to represent 4 different states, we require 2 bits. Okay, 2 bits is okay because the 2 bits can represent the 4 different values. Okay, I could 0, 0, 0, 1, 1, 0, 1, 1. But we can apply different methods of encoding. So and then the different actually we can use this encoding rule. So we can minimize the number of bits to represent different states. Also, we can use one-hot encoding. Okay. So one-hot encoding instead. Each bit of one-hot encoding represents the states. So what does that mean? So in this example, we have 4 states, and then in pin number 0 represents the state 0, pin number 1 represents state 1. So actually, in one-hot encoding, each bit each bit represents the different state. Okay, and so in order to represent the 4 different states, we require 4 bits for 1 hot encoding, or to implement 1 hot encoding for states. So, and then it's very, actually, I believe it's very simple. So it is because each bit represents the different state. But in order to implement the 1 hot encoding, we require more flip-flops, which means that we require more hardware resources. So compared to the binary encoding, the binary encoding requires two flip-flops, but with the 1 hot encoding, this 1 hot encoding requires 4 flip-flops. So 1 hot encoding requires more flip-flops. But if we use the 1 hot encoding, then we may generate simpler output logic. Simpler it may. Okay, so it means that we can use mono encoding method. We can select the binary encoding, or we can select the 1 hot encoding. So there can be different encoding rules for representing different states. So this is another example of the encoding rules for different states. So this is the example. So example of the previous Bohr FSM. So this is the state transition table, and then you can observe the different encoding rules. So I will use the 1 hot encoding. So S0 is the 0001, right? And then S1 is the 0010. So which means we can just change the state, the current state and next state using the 1 hot encoding rule. Okay, and that's it. So which means, so actually these are different states, and then we apply our own encoding rules for representing different states. Okay, but usually we can apply binary encoding or 1 hot encoding. Okay, and then let's see the example of Mealy FSM. Okay, so do you remember the meaning of Mealy or Bohr FSM? So the Bohr FSM means that the output is just determined by current state, and then in the Mealy FSM, the outputs are determined by current states and input signals. Okay, so this is the difference between the Mealy FSM and Bohr FSM. Okay, so let's see the example of the Mealy FSM. So actually, in this example, I will just compare the Bohr FSM and Mealy FSM for the same problem. Okay, so this is the example, the smiling signal. So this is the sequence of number. So you can find the sequence of number here at 0, 1, 0, 0, 1, 1. And then snail is crawling over this sequence of numbers. Okay, and then the snail can read the 0 and 1. Okay, and then if snail detects the sequence 0, 1. So sequence 0, 1. So which means that it is composed of the previous event and current event, right? So it's a sequence. So which means that we need to implement sequential logic, the previous event. So this snail, this smart snail will smile if snail detects the sequence 0, 1 of the number of sequence of numbers. So we can design the logic of this snail using the Bohr FSM and Mealy FSM. How? So this is this description. the description of problem, and then we can define, we can implement the raw FSM or Mealy FSM based on this description of problems. How? So firstly, we need to define input and output signals. So what are input and what are output signals? Input is numbers, the sequence of numbers. Okay, so number is given. The no. This is the module. So module you need to design. And then what is the output signal? Output is the smile. So it was snail. It is snail smiles, and it means 1, and if not, it's 0. And then what is the functional specification of this module? This one. So we need to detect the sequence 0, 1. Okay. Then how can we define this functional specification of this module? Okay, we define the input signal and output signal, and then this is the functional specification. So we need to detect the sequence 0, 1. Then how can we define the state transition of this module? It means that state transition of FSM. Okay, how? So we can choose raw FSM or Mealy FSM, right? So what is the input? So input is the sequence of numbers. So which means that, so this is the number. And then by time, you can receive different sequence of numbers like 0, 1, 0, 0, 1, 1, 0, 1. So in this example, we can detect this sequence, and this sequence. So firstly, we can consider the Moore machine. So in the Moore machine, then we need to detect the 0, 1, and then which means that we need to define the states that detect this 0, 1. So it means that we need to define states that is associated with the sequence 0, 1. Okay, how? So which means that if a sequence is 0, 1, we will detect the output will be 1. Otherwise, output will be 0. Okay. So how can we define the states? So actually, this is not easy. This is a little bit tricky. For Moore machine, for implementing Moore machine for this description of a problem, but we can define some different state like the S0, S1, S2. Okay. So and then based on some sequences, we can define the different states. So for example, S2 is the 0, 1 state sequence 0, 1. So which means that this is the output 1. And then S1, S0 is the sequence 0, 0. So we can define the two constitutive zeros here. And then not this one. So this is the sequence 0, 1. So it is the output 1. And then so this is the 1, and then this is the 0, and then not this one. So, which means that in order to detect the 0, 1, so this means that the previous states, previous numbers to be 0, and then current numbers to be 1. So, we consider the transition. So which means that the state is changed by the input signal. So which means that the state can be changed by this input. So we define the S2 is the output 1. And then which means that we need to define the different transition of 0 and transition, the sequence of 0 and sequence of 1. The input signal is changed to the this different state if we detect the 0. And then the state is changed to the S2, and S2 will generate the output 1. Then if we detect the 1. Okay? So which means that the Moore machine, Moore FSM, we detect the different transition of this. So which means that S1 represents that the previous input is 0, and then S2 represents that from the S1 the previous input is 0, then if 1 is given, then it changes to the S2. So we can detect the transition 0, 1. Okay. And then based on the base definition, then we can generate the state transition diagram. So actually, for this sequence, the Moore machine is a little bit tricky. Okay, so we need to define the state based on these different sequences, like 0 and 1. Okay, so state is changed to the S1, so which means that if the previous 0 is detected and is changed to the S1, and then in this state, if the input is 1, the state is changed to the S2, then output becomes the 1. So this is the Moore machine. Okay. But if we just consider the Mealy machines, the Mealy FSM, we can define the Mealy FSM more easily. Why? The Mealy FSM, so when we define the Mealy FSM, the output of the Mealy FSM is determined by current speed and input. So if we see the this sequence, what is the current input? Current input is 1. Okay. So which means if the previous state is 0, so it means that the previous input is 0. In this state, if the input is 1, then state is changed. So which means that the previous input is 1. But when the state is changed from 0 to 1, so it's the previous input, then output becomes also 1 because we can detect the 0, 1. Okay. So 0 means that the previous input is 0, then 1 means that the previous input is 1. And then if the state is changed from the 0 to 1, then the current input is 1, then output becomes 1. So this is the Mealy machine. The output is determined by current state and input signal. Okay. So let's see the example. So this is the state diagram of Mealy FSM. Okay. So there are two different states, and then S0 and S1. And then S0, actually S0 represents that it's the previous input is 0. So currently it's 0. And then S1 represents the previous input is 1. Oh, that's So this example is different. So actually this is 0 and this is the different state. This is 1. Okay. So let us assume that the initial state is 0. So it's the initialized state. So in the reset state, it becomes the S0. And then we can the state is changing between S0 and S1 based on the input signal. So in this transition, so you can find the two numbers, and then in these two numbers, the left side number is the input signal, and then the right side is the output signal. Okay. So if the 0 is received to this module, and then it is changed to the S1. So which means that we need to detect the 0 and 1. Okay, 0 and 1. So it means, if 0 is detected, then we can, based on the next input, then the output can be 0 and 1. So which means that this is the previous event. So the state can be changed. Okay. So in the Mealy machine, the output is determined by this previous input and then current input. So which means that based on the previous input, the previous result, then the state is changed. The 0 is input, then the state is changed. It's ready for detector 1. Okay, in the Mealy FSM. So if 0 is detected, then if you change the S1, it's ready for detecting next one. Okay. So in this state, the S1, if the 0 is received, then output is 0. Is it because the sequence is 0, 0, right? So output is 0, and then the state is changed to its old state. Because currently the previous event is also 0. Okay, it is the 0, 1. And then in this state, if the input becomes 1, then the output becomes 1. It is because S1 represented, this previous event is 0. So which means that we are ready for detecting next 1. So it's 1, and then out becomes 1. Because we can detect the 0, 1. And then if 1 is received, the state is changing because the previous event becomes the 1. Okay. So in this time, at this point, so even for the different input like 1, 1 and 1, 0, then the output is the same. We don't need to change it to this state, the ready for detecting 1. Okay, so it should change to the S0. So which means that the previous event is 1. So this is the Mealy machine. So which means that the output of this Mealy machine, Mealy FSM, is also determined by current state and input signal. But let's see the Moore machine. So which means that we need to detect the 0, 1. It's the same. So the firstly, if we detect the 0, so it's 0, then it's 0. But based on which means that we need to detect this sequence, the sequence of input numbers, okay, right? It's 0 and 1. So in the Moore machine, so S1 represent the ready for detecting 1 because the previous event is 0. Okay, so we need to detect this when it's two transition 0 and 1. So it means that it becomes the S2 and output becomes 1. Okay, so this S1 represents the ready for detecting 1, then S2 means that it becomes 1. Okay, so then we can define the state transition between states, different states. So in the Moore machine, we define this transition, the transition between here S0 to S0 to S1, and then S1 to S2, and then S1 represent the ready for detecting 1 because the previous event is 0. Then based on the input, then we can define the state transitions. So for this S1 input, if the next input is 0, it's same because the previous event is 0, it goes to the S1. Okay, so each means that it's ready for detecting 1 because the previous event is 0, and the 1 is here. So in the S2, the currently the sequence is 0, 1. So then if the next event is 0, so which means the input is 0, then it goes to the S1. But the 1 goes to the S0 because if the current input is 1, then we detect the 0, 1 again. Okay. If the previous, so if the 1 is detected, then we need to detect the 0, 1 again. Okay. So it goes to the 1. So it is a little bit tricky to define some states the Moore machine, but if we just define that as what, so S2 is the state that can make the output 1, then we can define the previous state as 1. It's the ready for detecting 1. Okay, that's 1. Then which means in the state transition, then we need to take the 0 and 1. So which means that we need to detect define the S0, the initial state. And then based on the input signals, then we can draw the state transition diagram. The Moore machine, the Moore FSM. So if you see the state transition diagrams of Moore FSM and Mealy FSM, you can find the difference. The difference is this one. Okay. Also, this one. In the Moore FSM, the output is just associated with the state, the current state. So it means that output is 0, the current state is 0 as 0. Output is 0, the current state is as 1. Output is 1. This sequence as 2, that's the sequence 0, 1, right? It's sequence 0, 1. Okay. So S2 is the state that can make output 1, and then S1 is the ready for the 1. Okay, we can define the 3 states like this. But in the Mealy FSM, so S1 instead is the also ready for detecting 1. And then the output is determined by the state and input. So we can observe the output signal here, not inside of the current state in the Mealy FSM. Okay? So it's a difference. The output is inside of the current state, it's Moore FSM. But if we observe the output and this transition between state and then it's Mealy FSM. Okay. So let's review the Moore FSM. So we define the two states as 0 and so on as 2. And this is the state transition diagram. And then we can define the next state based on the current state and input. Okay. So this is the encoding rule as 0, 0, 0, 1, 1, 0. So this is the 0. So the current state is as 0. And then based on the input signal, then state is changing. So from the S0, the input signal is 0, it's S1. So it's 0, 1, and then it's 0, 0. This is the current state is S1. So this is the if 0, the input is 0, then state is changed to the 0, 1, then it's 1, 0. Okay. We can fill the state transition table like this. So then we can define the output. We can define the next state logic. Okay. The next state logic. Then also in the Moore FSM, the output Y output is determined by current state only. The 0, 0, 0, 0, 1, 1, 0, 1, 0, 1, 0 becomes 1. So we can design the output logic. Okay. So this is the Moore FSM, but the Mealy FSM. So this is the state transition diagram of Mealy FSM, and then there are only two states. So we can encoding state S0 is 0, then state S1 is 1. And then it's simple. So you can find the current state here and then input A. So based on the current state and input, then next state is also changing. And at the same time, output is also combined. So based on the this current state and input signal, next state and at the same time, output is combined. So this is the Mealy FSM. Then how can you do this transition and output be simple, right? If we see that this transition diagram, then we can fill this table. So if the current state is 0, input is 0, so current state is 0 and input is 0. Then the next state is S1, S1, right? It's 1, then output is 0. 0, 1, the input is 1, so this is the input. The left, the arc, the transition, and left side number is input. So this is input. Then the next state becomes the S0, is 0. What is the output? Output is 0. And then the current state is 1 here, and the input is 0, 0, 0, equals to S1. So next state is 1, output is 0. Okay. So then 1, input is 1, then it goes to S0, 0, then it's 1. So the Mealy FSM, we define the next state and output is the current state and input. Okay. So this is the result. The next state logic is like this. This is the output logic. Okay. So actually you can find that the next state logic is A bar. So it's the inverse of input. So it is because if we just detect the input 0, then it goes to the S1. Okay. Because it's ready for detecting 1 for the next sequence. And then based on this truth table, so the transition table, output is 1, if the current state is 1, and then input is 1. This is and okay, and so we can implement the Mealy FSM like this, right? So this is the Mealy FSM schematic. You can generate the schematic based on this state transition table and then output table. Okay, so based on the state transition table, we can generate the next state logic, and then based on the output table, we can generate the output logic. So this is the Mealy FSM. So this is the next state logic SL, and then this is the output logic OL, and then this is the state register. Okay, and then Mealy machine. So you know, the Mealy machine, we have only one out and two state. So this is the state register, and then you can find the next state logic and then output logic. But the Mealy machine, you can find that the output logic, the input of output logic is connected to this is the current state, and then input. Okay, so this is the difference between Mealy FSM and Mealy FSM. Okay, but the operation is operation looks the same, but actually, if we just compare the time, if we just compare the timing of Mealy machine and then one machine, the Mealy FSM and Mealy FSM, timing is a little bit different. Why? It is the time is a little bit different, right? Because in the Mealy FSM, the state is changed by input. Okay, but you know the state. If we see the state register, the state is changed at the rising edge of the clock, right? So when we detect the input 1, okay, then state is changing to the next state 2 at the rising edge of the clock. Then output is generated. So which means when the current state becomes S2 at the rising edge of the clock, then output is determined. That is the Mealy FSM. But if we see the Mealy FSM, the Mealy FSM, the output is becomes 1 when input becomes 1. You understand? So based on the input, the state is changed, but out at the same time, the output is changed. Okay? Which means that when the input is changed to the 1, and then at the same time, with some delay, because it's a combination logic, but at the same time, output becomes 1 immediately. So you need to understand some different timing between Mealy and Mealy FSM. So the Mealy FSM output is determined by current state only, but current state is changed at the rising edge of clock. So actually, when the sequence becomes 1, and then after the rising edge of clock, the output becomes 1. This is Mealy machine. When the Mealy machine, the output becomes 1 with the input change. So output is changed immediately if input is changing. This is Mealy machine. So timing is a little bit different. So actually, we read the same tabular description then actually based on the same problem description, we can design the more FSM and Mealy FSM. The output is same, so input 0, 1 is detected, and the output becomes 1. But based on the different type of FSM, timing can be different. This is because, as I mentioned, in the more FSM, the output is associated with the state only, and then state is the output of flip-flop. But in the Mealy FSM, the output is the combination of input and state. So which means input is changed, output is changed immediately. Okay, that is the difference. So let's see the timing diagram of Moore FSM and Mealy FSM. So this is the input sequence 0, 1, 0, 1, 1, 0. So and then we can also find the changeable state here. But if we see the output here, then we can find that in the Moore FSM, the output is changed at this time. Right? This time. Right? But if we see the Mealy FSM, the output is changed here, here, here. So you can, I believe you can observe the difference. So why? If the 0 is here, then 0 means that if a number 0 is received to this module, then it goes to the ready for detecting 1. Okay, so it's the same. Actually, it goes to the S1 and S1. Okay, ready for detecting 1. Goes to the 0. The state is changed to the S1 and S1, and then input becomes 1. The Mealy 1 is detected, and output is changed immediately. Okay? Because the current state is S1. So we can find that S1. So we can find that output becomes 1 immediately. Okay. But the Moore machine, then 1 is detected, then state is changing. The output is actually synchronized with the state. Okay. So then state becomes S2, output is changing. Okay. So timing can be different between the Mealy machine and Moore machine, the Moore FSM and Mealy FSM. So I showed the two different examples, and two different FSM implementation examples, the Moore and Mealy. So it can be implemented from the same problem description, but then the transition diagram is different. Also, the timing can be different. Okay. So there are two different methods for implementing the FSM. And then let's see the vector FSM. What is the vector FSM? So we can divide the complex FSM into multiple simpler FSMs. That is the vectored FSM idea. So this is just an example. So this is the modified problem description. So it's a traffic line, traffic sign, and then we added the more condition, the parade mode. So it's a more condition in parade mode. So parade mode becomes P equal 1. It goes to the parade mode, and then rubber becomes green, regardless of the output of traffic sensors. Okay, so if we start from this example, we'll see this example. Okay, the traffic sign example. So it's a Bravado, Billboard, and then Academic Avenue. And then it's a the polarized mode becomes 1, then regardless of the output of the sensors, then Bravado, the traffic sign of the Bravado becomes green. Okay. And then if R is 1, that means that if this is the end of the polarized mode, then the state is changed to the normal state. So we can define two more inputs, P and R. Okay. And then we can, which means that this is the new module. And then this new module is in the two more input signals, P and R. And then also the output is the same. Output signal is the result of traffic light and traffic sign. So P and R can be exposed to the control FSM. But we can design FSM like this. So it's a one very complex FSM. But we can just divide the FSM into two different FSM. It's the mode FSM and this is the light FSM. And based on the P and R input and mode FSM determines the mode, operation mode of this light FSM. Then based on this other input and the light FSM defines the traffic sign. Okay, let's see the example. So this is the unfactored FSM. So this is the FSM of this module. This module receives the 4 input signals, and then based on the input signals, and then we can generate the traffic sign. It's so complex, you know. So there are how many? 8 states. Then we can find a large number of state transitions. Okay, so it means that it's very difficult. It's very difficult to design the state transition of this system. Okay, but if we read the conditions of the system, so actually we can, if we read some descriptions of the problem, then we can know that based on the P and R, then it goes the polarized mode and then it ends polarized mode. So it means we can just define the mode, operation mode of the traffic sign, okay, based on the P and R input. So we can divide the FSM like this. So first FSM is mode FSM determines the operation mode, then the mode is given to the light FSM. Then we can define the state transition of these two different FSMs like this. Okay, so this is the mode FSM works with the P and R input, and then mode FSM generates the operation mode signal output, and then this is the modified light FSM. So we can find the another input M here, okay, and then based on the operation mode, the light FSM is also modified, but it's much simpler than the previous example, right? So usually the systems are very complex. The modern systems are very complex. So which means that our module receives the many inputs. So which means that and then based on this many input signals, we can define many different states. But it means, so if the system becomes more complex, it means that it becomes more difficult to define state transition, the states of the FSM. Okay, so we need to simplify some conditions, which means that we can divide the problem size. Okay, Then how can we divide the problem size? So which means that, so in this example, we can just divide the problem size in problem into the two problem, like the operation mode, then normal mode based on the input signals. And then based on this operation mode, then we can define the normal FSM, so that's the right sign FSM. Okay. So if we divide the problem size, then we can design FSM more simply. Okay, so it's also same for the real. It can also apply to the real world problem. So our real world problems can be very complex. So very complex. So it means that there can be many conditions, many different conditions and many inputs. So in this case, we can divide the problem size based on the different conditions, right? Then we can simplify the some systems into the smaller systems, right? And then we can define the operation of the smaller systems. And then these smaller systems are connected with each other. And then we can design the very complex top system. But this approach, if we apply this approach, then the problem becomes simpler. Okay. Again, so vectoring idea, the vectored FSM. With the vectored FSM, we can design the simple FSM using by reducing the size of problem. And then we can define more efficient system. Okay. Okay, so for this FSM, please read the textbook chapter 3.4. Then we have 7 minutes. Okay, so another but it's just the review of the latches and flip-flop. So now, so we will learn about the audio description language is the system value. So actually until now, so we learned about the combination of logic design with system value. Now it's time for learning about sequential logic design with the system value for latch and flip-flop. So we already learned how to design latches and flip-flops with system value, right? So this is the latch. So just memorize the definition of the latch. Okay. And then we can use the always on the latch to define the latch. So this is the if clock, then Q becomes D. So it is called the level sensitive. Level sensitive. So it is because so latch is a level sensitive. So it is because if clock level becomes 1 or 0, then the operation mode is changed. So it is called the level sensitive. The clock is 1, then Q becomes D. It's not, it's a memory. And then flip-flop. So we can say that flip-flop is the edge sensitive, right? So it's a level sensitive and it's edge sensitive. And then we also already know how to implement the flip-flop, flip-flop. So the positive edge of clock and Q becomes Q. So it is edge sensitive. Okay. And then as I mentioned, we can use arrays. Okay. So which means that if you just remove underbar effect, it's okay because system value also includes the syntax of value. So which means so actually value has only always statement, or system value has 3 different always statement, always count, always effect, and always match. But if we just remove the underbar effect, it's okay. It's fine. So this is the flip-flop design. So this is the enabled flip-flop. Then also so asynchronous reset and the flip-flop is the asynchronous negative reset. Okay, so negative reset here. So okay, So this is the flip-flop and latch design. Okay. And then the next class, we will learn about the blocking and non-blocking assignment. So actually, this is the important part of the Verilog design because our hardware design is a little bit different from the software programming, and then this blocking and non-blocking explains the main differences between software and hardware description language. It is because some students notice that I sometimes use the equal sign, but I also sometimes use the, how can I say, this arrow sign. Okay, but the meaning is different. Okay, I'll explain about the different meaning of this different sign, assignment sign. Okay. Okay. Thank you for your attention. And see you in the next class. Come down.